Okay, so today, guys, we're going to go over the last half of chapter 5. And again, in your notes, it might be called like 5.2 to 5.3 or 5.3 to 5.4. Comparing the homework and, whatever. Just keep in mind that this is the second half of chapter 5. So binomial probability distribution. So we're up here. And it says that this section focuses on a specific type of discrete probability distribution called binomial probability distribution. So this is countable probability distribution. Binomial probability distribution allows us to look at situations where there are only two possible outcomes of an event. So yes, no, heads, tails, defective, acceptable, positive, negative, survived, died, etc., so on and so on and so on. So we've done problems like this already. When we did the one where they had type A blood or not type A blood, that was technically binomial because there was only two outcomes. So there's a bunch of different things that we need to account for. So there are a fixed number of observations, check. The n trials of observations are independent events, right? Each trial must have an outcome classified in one of two possible categories, commonly referred to as success and failure. So again, don't think of success and failure as good and bad. Just think of it as success is what you're looking for and failure is not what you're looking for. The probability of success is labeled as P and is the same for each observation. And the probability of failure is labeled as, or is the complement, which is Q, which is 1 minus P. So example, set up 10 coin flips of a fair coin, okay? So first thing is, this is 10 times, I'll write it in black. So 10 times, so it is a fixed, let me make this a little bit smaller. Fixed number of trials, okay? And that equals n, which we know is 10. They're independent because since one flip does not affect the next flip probability. Okay. Geez, this is kind of, it didn't line up quite right, you guys. I guess when I copied the pages, something went wrong in the transition. Sorry about that. So I'll just do step 3 right here. Has two possible outcomes. Right? Heads or tails. Okay. And 4, and depending, one is success. So this could be called the success and this could be called the failure for this particular problem, and it could flip the other way. Let me write this. And then part 4, we could say the probability of success. So we'll say probability of heads equals 0.50 and probability of tails equals 1 minus 0.5, which is 0.5. So we have the two labels for our oops. So this could be, I'm sorry, I should have written it like the book did. P equals 0.5 and Q equals 0.5, okay? Just because it's 50-50, it's a fair coin, okay? So that's just kind of reviewing that idea. So the binomial random variable x equals the number of success observed in the independent trial. So we say P of x, the probability of getting exactly x successes in independent n trials. Since x is the number of successes in binomial setting, x can be any whole number from 0 to n. So like I think also in the jury question we did, it was either the jury was Mexican-American, the juror was Mexican-American, or they weren't. So that's binomial. There was a fixed number of trials, 12, right? You had 80% for success and 20% for failure. So we basically had everything we need. And it was independent because they didn't tell us the size of the population. So we treated it as independent because it was very large. We're assuming it was large. So genetics says that children receive genes from their parents independently. Each child from a particular pair of parents has a 0.25 probability of having type O blood. If these particular parents have 5 children, the number of children that have type O blood can be represented by the random variable x. Show why x is binomial variable and check the requirements. Okay, so let's take a look at that. So first thing we're going to check, we're going to kind of go down our list. Remember, we have 1, 2, 3, and 4. So first thing we want to know is 1. Does it have a fixed number of trials? Yes, they have 5 kids, 5 children. So check. Step 2, or I'm sorry, n equals 5, right? Let me see here. The second part would be, are they independent? Yes, independent. One childbirth does not affect the next childbirth. So independent, check, since one birth does not affect the next. Okay, now step 3. Step 3 is, let's go back up here. Each trial must have an outcome classified in one of the 2 possible success and failure. So we're going to call type O blood success. Okay, so let's see here. Probability P equals 0.25, and Q would be 1 minus 0.25, which would equal 0.75, right? So success and failure. And then we do part 4. Part 4 says, oh, that was part 3. Sorry. That was actually part 4. Part 3 was just saying that two outcomes, either type O or not type O, okay? And then we have P is equal to 0.25. So Q is equal to 0.75 because we just do 1 minus. So check, check, and check. So everything checks out. What are possible values for X? X could equal 0, 1, 2, 3, 4, or 5, right? Because there could be 0 children with type O, there could be 1 child with type O, 2 children, 3 children, 4 children, or 5 children with type O, okay? Okay, so now let's go back to this juror question. Again, you're going to see something like this on the midterm or on the exam. So 12 jurors are randomly selected from a population in which 80% of the jurors are Mexican American. Again, they didn't tell us the size of the population, so we're going to assume it's large. So that means taking 12 people from this population can be treated as independent events because it won't affect the probability of the next draw too much. So if we assume jurors are randomly selected without bias, and if we let X equal the number of Mexican American jurors among 12, show why X is binomial variable, check the requirements. So once again, n equals 12, check. 2, independent, check. 3, one juror chose, by the way, I don't want to write it all out, but one juror chosen does not affect the next juror's probability of being chosen. And then number 3 would be, how do we set this up? 2 outcomes. Mexican American juror or not. That's pretty much the 2 outcomes. Then we have number 4, probability of P is equal to 0.8 and probability of not P is equal to 0.2. What possible values for X are there? So once again, there's a lot, 0, 1, 2, all the way down to 12, right? So there's all of these 0 through 12, okay? So there's 2 methods that we're gonna use to find these probabilities. Remember, before, way back here, we didn't know how to find these probabilities. They had to give us this table. So now we're gonna be able to find these values ourselves without somebody handing us a table, okay? So the first method is using the binomial probability formula. I am not gonna have you guys do this by hand. I'm gonna have you guys use your calculator to do it, okay? But basically what it does is, this should look familiar to you, okay? That's from our permutations and combinations, I guess, formulas. And then we have something like this. I believe this was for combinations. And then we multiply this by the probability of P to the power of X, how many successes, okay? And then times the probability of P to the leftovers that were not the successes, that were the failures, okay? So this value right here is called the binomial coefficient. We're not gonna spend too much time on this. But we can do, so the NCX, that was from our formula from the beginning of chapter 4, from the end of chapter 4. Okay, so let's do this problem now and let's find whatever they ask us for. So we're going to identify P, we're going to identify Q, and we're going to identify N. So we know that this is 0.80, we know this is 0.20, and we know that N is worth 12. Okay. Now it says find the probability that we get 7 Mexican American jurors, exactly 7. So that means probability that X equals 7. Now, if we want to go back and look at the table, that's fine. But what if we didn't have the table? So according to the table, exactly 7 should be 0.053, so about 5%. Okay, so we're going to come here and we're going to try to figure this out on our own without using the table. Okay, so what I'm going to have you guys do is I'm going to have you get out your calculator. Okay, and for all of these, we're going to use our calculator. Okay, I'm not going to require you guys to do it by hand. But in the homework, they might show you, like if you click on view an example, they might have you do it by hand. Well, you know what? I guess we'll do this first one by hand just so you guys can kind of see it working like that. Okay, let me see here. Oh no, I did it in my notes. I did it on the calculator as well. So let's just go from the calculator. So the probability that X equals exactly 7, okay? So you have to take out your calculator and you have to find the function that says binomial PDF, okay? So right here, this is what you're gonna see on your calculator, binomial PDF. So the way you get there is you go second vars distribution. So I'm gonna take out my calculator and I'm gonna go second function. And then right here, you see this vars button that's red now? You go to that and then you go down until you find the one that says binomial PDF. So you use binomial PDF for exactly, and you use binomial CDF for cumulative. So when you want to add up all the values that came before, okay? So I'm going to click enter on binomial PDF. Now it wants to know how many trials. Well, I know there was 12. What's the probability of P? Well, that's 0.8. What's the X value? How many jurors are we looking for that are Mexican American? We said 7, exactly 7, and then you hit enter. So now you have binomial PDF, and I hit enter and I get 0.053, same as the table. So let's go back here. So you do binomial PDF 12, comma, 0.8, comma, 7, and we get approximately 0.053, right? So this is how you can do it, and this is how you can show your work. All you have to do is write out what the calculator, what you're entering in on the calculator, and you're good, okay? So we're not gonna use this formula very often, but the calculator is basically, when you hit enter on the calculator, it is doing this right here. It is doing that formula right there, okay? So that's what it's doing. That's why it wants to know X, that's why it wants to know N, and that's why it wants to know P. It doesn't need to know Q, because if it knows P, then it technically knows Q is 1 minus P. So it knows how to do all that. It's been programmed that way. So we're going to use that to find that. So what we're saying is the probability of getting exactly 7 jurors that are Mexican American out of 12 is 0.053. And they're taking into account all the scenarios with this formula. There's all these different situations that could create 7 jurors that are Mexican American. The first 6 could be Mexican American, then the next 5 could not be, and then the last one could be. That would be, I'm sorry, the first 6, and then the next 5, and then the last one could be, right? So that would be 7. Then you could do the first 2, not the next 2. The next 2 are, the next 2 aren't, then the next one is, and then the next one is not, or whatever. So you could have, 7, a bunch of different ways. So there's no way we could possibly write out all the situations like we did with the tire problem or with the Skittle problem. So what we're doing instead is we're using this formula to account for all the possibilities. And that's what this first coefficient helps us do. This NC, N choose X, tells us how to deal with all the number of possibilities. Then we multiply it by their probabilities respectively, okay? So the calculator will do all that for us in the formula. So it says find the probability of at least 11. So probability of at least 11 of the 12. So that means X is greater than or equal to 11, right? So this would be the probability of X equals 11 plus the probability that X equals 12, okay? So what we do is we do binomial PDF, and then we do 12, comma, 0.8, comma, 11 plus binomial PDF of 12, comma, 0.8, comma, 12, right? And let's see what we get. So we're going to go on our calculator. We're going to go second function. Oops, not second function. We're going to go vars. Oops, second function vars. Then we're going to go to binomial PDF. Remember, PDF is for exactly. Okay, and we're going to do 12. Wait, why is it doing it different this time? Second vars. Last time it did it nicer for me, right? Yeah, there you go. So 12, comma 0.8, but this time we're going to do 11. And then we hit enter, and it gives us 0.206158. So I'm going to do 0.02168. I'll just use a few extra decimals. I'm going to show you guys what I'm going to do instead. Then I'm going to hit plus. So it's going to take that previous answer, and then I'm going to do second vars again, and I'm going to go binomial PDF. And then this time I'm going to do 12. So now it's going to tell me the total. You know what? I kind of screwed that up because I wanted to show you guys the both values. So let me quit and clear. Second vars. Let me do one value after the other. So this one, and then let's do this again. So this is actually 0.0687. So plus 0.0687-ish. So this one is that, and this one is that. And then when we add these up, so I'm going to take this plus second vars. I'm going to go binomial PDF, and then I'm going to go down to, 11. So it's going to add the 2 up now, and that'll give me the 0.2748. So let's just say 0.275 for now. So this will be approximately equal to 0.275. So that's the probability. Now there is a faster way to do it, okay? We can use binomial CDF. Now binomial CDF adds up everything that comes before. So an alternate way we can do it is we can do binomial. So let me write this again. So the probability that X is greater than or equal to 11, we could have done it this way. We could have said 1 minus the probability that X is, here's a better way. Binomial, let me kind of talk to you guys about what this does. CDF of 12, 0.8, 10. So what you're telling the calculator when you're doing binomial CDF is you're telling it to start at 0 and add up to wherever you want it to stop. So I'm going to have this add up all the probabilities from X equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So what are the only 2 probabilities that I did not add? I did not add 11 or 12. So these 2 are being left out. So if I do 1 minus the first 10, then the only 2 left should be this value right here. So I'm going to go, so that's what CDF does, is it starts at 0 and adds up until you tell it where to stop. And the reason I can't tell it to stop at 11 is because that means it would also be including 11 in its probability. And then when I do 1 minus, the only thing left would be 12. So let's try this. Let's go second vars. Binomial CDF. So we do 12 trials. We do 0.8 for that, and we're going to stop at 10. We're going to only have it add up 10. So we hit enter. Now I do 1 minus this answer. You do second function answer, and I get 0.275, which is the same answer that I got over here. Okay, so this is the same probability that I get from doing it this way. So normally this way is for when you're only doing one of them. So I would have probably done the binomial CDF one. So what if I asked, find the probability that X is greater than or equal to 8? So that's going to be rough if you try to do it this way, right? Because that means you have to do 8, 9, 10, 11, and 12. So what I could do instead is I could say 1 minus binomial CDF of 12, comma, 0.8, comma, and then I'm going to go up to 7. So I could do second vars, where's it at? Do binomial CDF, but this time only go up to 7. Okay, that was the right one, right? I said 8. Yeah, so because I'm going up to, I want to find out all the values 8 and above, I do binomial CDF up to 7 and then subtract it from 1. So I did binomial CDF up to 7, and then I do 1 minus second function answer, and that gives me 0.927. Okay, or almost a 93% chance that this is going to happen. Okay, so these you should write down on a little cheat sheet to help you with calculators, because this will be very important for binomial PDF or CDF. Remember, this is for exactly, and this adds up, I guess, previous probabilities. Okay, so then it says find the probability of 7. I think we already did that up here. Yeah, so I basically, this is same as above. I use the calculator for both of these, so don't stress about that. And then same as above. So this is just happening twice. Okay, so I would prefer to use a calculator for all of these. Again, that formula is a little difficult to deal with. So now let's talk about mean and variance and standard deviation. And again, guys, I don't mean to gloss over this. You really need to learn how to use your calculator for this. It makes the problem so fast. If you're trying to do it all by hand, you're going to run out of time. Okay. So mean, variance, and standard deviation. In this chapter, we learned that 3 general formulas to find the mean, variance, and standard deviation for discrete probability distribution. While those formulas can be applied to any binomial distribution, since any binomial variable is discrete, finding the mean, variance, and standard deviation of binomial distributions have shortcuts. So these are much nicer formulas than I showed you in the past. You just take the n times p, you take n times p over q, and you take the square root of n times p over q to find standard deviation. Okay, and then we can use the same stuff that we've been using to find our minimum usual and our maximum usual. Okay, so let's revisit this jury problem again. So it's the same exact problem. It says find the mean and the standard deviation for the distribution of x equals number of Mexican American jurors. So I'm going to find the mean. So I'm going to find mu equals n times p. In this case, n is 12 and p is 0.8. So all I do is I take my calculator and I do 12 times 0.8. So it's 9.6. So that means that in general, we should expect to have about 9.6 jurors. So either between 9 and 10 jurors that are Mexican American on this jury, because it's 80% population is Mexican American that you're choosing from. So anything outside of 2 standard deviations away from that, we would consider unusual. And then for the standard deviation, so standard deviation would equal the square root of 12 times 0.8 times 0.2. So I take out my calculator and I do second function square root of 12 times 0.8 times 0.2, and I get approximately 1.386, let's say. Let's just use 3 decimal places on that. So 1.386. And it says compare these values for mean and standard deviation to the values when we found them using the other formulas. Are they the same? So we come back up here. I don't know if we actually found it for that one the old-fashioned way. I want to say we didn't. Yeah, I don't think we did. Maybe I should have somewhere. So that's probably something you guys should make sure you know how to do, is remember, you take to find the mean, you would have to do it the old-fashioned way, right? You would take this times this, we get 0, 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 this times this, we would get 0.004, this would be 0.015, you know, so on and so on and so on. Like I did in, I think I did it in this one because it was shorter. Yeah, this one was easier to do than doing 12. So that's something you guys can work on. But what you'll see is it'll be pretty close to the same. Let me double check and make sure. I think I actually have it written down. Yeah, so what I'll do is I'll write it out for you guys right here. I'm not going to go through and do it all by hand for you. I'm just going to kind of show you what you would get. So this would be what? 0.004, 0.015. This would be 0.096. This would be 0.071. This would be 1.064, I believe. 9 would be 2.1242, or no, 2.14-ish. This would be 2.83. This would be 2.266, and this would be 0.828. So if you add all of these up, you would end up getting 9.598-ish, give or take, okay? Then if you try to do the standard deviation, or the x squared times p of x, which would be the variance, this would be 0, 0, 0, 0. This would be 0.1016. This would be 0.075. This would be 0.576. This would be 2.57. It's either 77 or 97. I'm going to say 97. This is going to be 8.512. This will be 19.116. And again, this is a little bit of overkill, you guys. I wouldn't give you one this long that you have to do by hand. And this would be 24.926, I believe. And then this one would be 9.936, if I can read my writing here. And if you add all these up, you get 94.054, and then to find the standard deviation, you would square root 94.054. So second function, square root of 94.054, and we get 9.69. That doesn't sound right. Let me see, how did it tell me to find this? Did I do it wrong? No, that should be right. Let me double check something, guys, in my notes. I can't read the writing here. Okay. Last page. Okay. So yeah, so our standard deviation is much different than the one that we would get from that. So we come over here, and unless so the square root oh, so no, never mind. Remember when we do this, we have to, I forgot to subtract off the mean squared. So we do this up here. Sorry, I had the wrong formula. So we get 94, right? And then if you want to know the standard deviation, you have to take 94.054 minus the mu squared, which would be 9.598 squared, and then you square root that. Okay, so if I do that, I get 94.054 minus 9.598 squared, and then I square root that. I get 1.39-ish for my standard deviation, okay? So when we compare that, to our standard deviation, way over here, we compare that to our standard deviation right here, I get 1.386. They're pretty close. Are they the same? No, they are not the same, but that could be to rounding error. But they are very close. And remember, way back up here, when I was doing these calculations, remember for this table right here, see all these zeros, zero pluses? Those aren't actually zero pluses. Those are simply close to zero, and we didn't account for them. So that could attribute to some of the miscalculation and rounding off incorrectly, or maybe too early, okay? So let's look at this last problem here. It says, find the maximum and minimum usual values. Is it unusual to be only 3 jurors that are Mexican American? Well, I'm pretty sure I can tell you right now that that is very unusual. But what we're going to do is we're going to use our rule of thumb. So we're going to find the min usual and max usual. And remember, the min usual is the mean, right? So I'm using this formula right here, is the mean. So we said that the mean was 9.6 minus 2 times 1.386. And this is 9.6 plus 2 times 1.386, okay? So let's see what we get. Okay, so when I enter this in my calculator, 9.6 minus 2 times 1.386, I get 6.828. So that's the minimum value, so close to 6 or 7 jurors that are Mexican American. And let's do 9.6 plus 2 times 1.386. That should be 12.372, okay? So this is basically approximately 12, because you can't have 12.3. So that means that it is, yes, it is unusual for only 3 jurors to be Mexican American on this jury, okay? Because you're taking from a population of 80% Mexican American, you would expect to have about 9.6, right? Because remember, the mean is like the expected value. That's kind of our expected number of jurors that should be Mexican Americans. And so about 9 out of the 12, maybe even 10 out of 12 when you're drawing from a 80% population, okay? So let me see here. It says the NSHC website states that 47% of all Americans are over, I think it's National Science Health. I don't know what that stands for, actually. Suppose we were randomly select an American town that has 40,000 people. It said 47% are overweight right here, right? So it says, what are the mean and standard deviation for the number of overweight people in a town of 40,000? Okay, so they're either over or they're not. So that's binomial, okay? So our N is equal to 40,000, right? Our P is equal to 0.47. So that means our Q is worth 0.53. So we have everything we need to find the mean. So mu is worth N times P. So this is going to be 40,000 times P, which is 0.47, okay? So then when we type this in our calculator, we should get approximately, let me do 40,000 times 0.47. And I get 18, I guess it's not approximately, it's exactly 18,800. So our mean is 18,800, okay? Now we can find our standard deviation by doing the square root of N times P times Q, which would equal the square root of N, which is 40,000, times P, which is 0.47, times Q, which is 0.53. So we will end up with approximately 99.820. So I'm going to put 99.820 right here. Okay. So we have a mean of 18,800. So that means approximately 18,800 people should be what we estimate to be overweight. And again, the mean and the estimated, or I'm sorry, not estimated, expected value are the same. So we're going to say that's about 18,800, and with a standard deviation of almost 100 people. Okay. So that's how you can use this instead of look how much faster this and this is than having to do this. Look at all of this that I had to do right here. Right? So I was just telling you the answers, but technically you have to multiply all those out and you have to square them and do all that stuff. So knowing it's binomial and finding the mean and standard deviation with binomial distribution is much easier than just regular distribution, okay? So that's going to do it for this section, you guys. Please show up to class with questions about the homework or anything like that, and we'll discuss it. Thanks for watching, and I'll see you in class.